Hello and welcome to our next tutorial on VOR movements and the associated neurology that makes the vestibular movements or movements of our head translate into counteracting movements of our eyes. So in today's video, what we're going to do is we're going to discuss another vertical pathway. This time we're going to discuss what happens whenever our chin moves vertically, but in the upward direction. So whenever our chin pitches upward. So let's go ahead and take a look at our neurology diagram over here. And just like always, we're going to start with the excitatory pathways, and then we'll work on the inhibitory pathways. I'll start with one side of the VOR, one side of the semicircular canals being stimulated and their associated connections, and then we'll work on the other side. So again, I like to do this in a stepwise approach. I try to do things the same way every time, and it makes it less likely for me to make mistakes in the pathway. So the first thing that I like to do is whenever I'm thinking about which direction is my head rotating, which direction or what is being stimulated and how are my eyes moving, the first thing I think of is upward chin acceleration results in the posterior semicircular canal being stimulated, or UPC. So upward chin, posterior canal is being stimulated. I also think of what are my eyes doing? So with the VOR movements, the pathway is designed such that our eyes are able to maintain fixation no matter if our head is being jostled around because we're walking or if it's moving up or down in this situation. So in this case, since our chin is moving up, our eyes need to move down to compensate for this movement. So the next thing that I like to do is try to figure out, well, what muscles are responsible for depression? And that's pretty easy. That's going to be the inferior rectus and the superior oblique. And it's going to be that way for both sides, because as the chin moves up, both eyes have to move down. So inferior rectus and superior oblique in both eyes are going to be stimulated to make our eyes rotate downward and stay on that target. So now we know a few things. We know which canal is being stimulated. In this case, it's the posterior canal, and so I'll denote this with a P back here. And we know which muscles are being stimulated up here in the orbits. So how do we make the connections here? Well, the next thing that I like to do is once I know which canal is being stimulated and which muscles are being stimulated, I like to think about which cranial nerve nuclei are responsible for stimulating those muscles. So we know that the inferior rectus is pretty straightforward. So it's going to be ipsilateral stimulation, which means that its stimulation had to come from this particular cranial nerve nuclei right here. And so in this instance here, this signal had to travel from this particular cranial nerve nuclei. If we stay with the right eye, or if we stay with the connections here for the right eye, then we need to know where did the superior oblique connections come from to get here. And so we know that these connections had to in fact come from the trochlear nucleus over here on the left side. So the trochlear nucleus has to receive some amount of innervation, and it's going to send those signals via the cranial nerve 4, which exits the brainstem dorsally and then decussates and crosses behind the brainstem and then comes back around the front anteriorly to in fact innervate that opposite or contralateral superior oblique. And so if this is happening on this side, the same thing is happening but opposite on the other eye. So cranial nerve 3 here is sending out connections to its own ipsilateral inferior rectus. Trochlear nucleus here sending out connections to its contralateral or to its superior oblique on the contralateral side, just like so. So now we in fact know which muscles are being stimulated, which cranial nerve nuclei are doing the stimulating. And now what we need to know is how did the signal get from the posterior canal back here all the way up to these connections? And just like before, this is really something that you have to memorize, unfortunately. So the posterior canal and all of the semicircular canals have multiple neurons that connect up to their cranial nerve nuclei. The one thing they all share in common is that after the semicircular canal, the next stop is going to be the vestibular nucleus. Now, could be medial vestibular nucleus, could be superior vestibular nucleus, but we know it's going to make its next connection here in the vestibular nuclei here. After that, then we have to try to memorize, what's going on here. We have to remember where our connections going. Are they staying ipsilateral? Are they going contralateral? But after we leave the vestibular nuclei, things change a little bit for each pathway. But the one thing that is constant is the first stop is the vestibular nuclei. So I'm going to draw my connections here from the posterior canal to the vestibular nuclei here. And in this case, the connection that's made is going to be the medial vestibular nucleus. And so these connections are going to synapse in the medial vestibular nucleus or medial portion of the vestibular nuclei. Now, you'll remember that the vestibular nuclei is located in the layer of the medulla in the brainstem. You'll also recall that cranial nerve 3, or the oculomotor nucleus, and the trochlear nucleus are located in the midbrain, which is superior to the medulla if we're thinking from an anatomical perspective. And so it's got to go up past the pons and then get to the midbrain. So these are the connections that we need to know. How does it get there? Is it via the MLF? Is it via some other pathway? And in fact, the pathways for the posterior canal do utilize the medial longitudinal fasciculus. However, they do so by crossing over. So they're going to cross over and they're going to ascend up the medial longitudinal fasciculus to the layer of the midbrain. Now, for ease of drawing this, I'm going to kind of make this look a little funky where it comes out around the side over here. That's just to make sure that we don't start getting jumbled up connections here right in the middle of the brainstem. So we're going to have the nerve going from the medial vestibular nucleus on the right side. It's going to decusate or cross over to the left and then ascend the MLF to the layer of the midbrain. Once it gets in the midbrain, it will exit the MLF, and then the nerve itself is going to split into two divisions here. One division is going to innervate the trochlear nucleus on the left side. One is going to continue forward and innervate the oculomotor nucleus, again on the left side. So now we have all of our connections. We have our posterior canal is sending out a signal via the vestibular nerve and the vestibulocochlear nerve, which are then going to synapse with neurons in the medial portion of the vestibular nucleus. Those signals are then going to decusate, cross over to the other side, and ascend via the MLF to the layer of the midbrain, where they will exit the MLF and then split into two nerves here, or split into two divisions. So once it splits, one layer, or one division of it rather, is going to go to the trochlear nucleus on the left side, and one division is going to go to the oculomotor nucleus again on the left side. To reach their respective muscles, the oculomotor nucleus is going to send signals to its own inferior rectus on the left side. But the trochlear nucleus, as you know, sends signals out to the contralateral superior oblique, or contralateral to the trochlear nucleus. So it's going to send signals out to the right superior oblique over here. Remember, those exit the brainstem posteriorly, cross over, and then go back or start to wrap around the brainstem and head anterior so they can enter the orbit with the other cranial nerves and innervate the superior oblique. So this is in fact the pathway for the right posterior canal. Remember, the chin is accelerating upwards, or the chin is moving upwards. Upward acceleration results in posterior canal stimulation, or UPC. And these are the EOMs that are in fact innervated. So if the right posterior canal is stimulated, it's going to result in the left inferior rectus and the right superior oblique being stimulated by that specific canal. Now, if we look at the left canal, because when the posterior canals are stimulated, or whenever the chin is moving in an upward direction, both posterior canals are going to be stimulated. So the left posterior canal is also stimulated here. Let's make a simple P there. And its connections are going to be the exact same. So it's going to travel from the posterior canal to the medial portion of the vestibular nucleus and synapse. The next neuron in the chain is going to leave the vestibular nucleus and cross over, or decusate, and then get into the MLF on the opposite side and ascend to the layer of the midbrain. Once it's in the midbrain, it's going to exit the MLF, and it's going to make connections in the specific oculomotor nucleus that it needs to in order to elicit that depression. And so it's going to synapse with the trochlear nucleus, and it's going to synapse with the oculomotor nucleus. The trochlear nucleus, it's going to control the superior oblique, and in the oculomotor nucleus, it's going to control its own inferior rectus. So if we can just follow this out here, then just act like we're kind of following these pathways again. The signal came from the left posterior canal, synapsed in the medial vestibular nucleus here, and then utilize the MLF, decusated, crossed over, utilize the MLF to ascend up to the layer of the midbrain, exits the MLF at the layer of the midbrain, and then it's going to split into two divisions, and it's going to innervate, according to the canal, the contralateral trochlear nucleus and contralateral oculomotor nucleus. If we just stay on the oculomotor nucleus for a second, the oculomotor nucleus is going to send signals to its own inferior rectus. The trochlear nucleus is going to send signals behind the brainstem, decusates, and then it proceeds anteriorly to innervate the opposite eye's superior oblique. So in fact, this is how the neurons, or this is how the EOMs rather, are stimulated whenever we have upward chin rotation and the eyes need to move down. And this again is the excitatory pathway. So for the vertical pathways, make a quick change here in color. So for the vertical pathways, according to Lee and Z, the same neurons, or the same semicircular canal rather, that's excited by the upward chin rotation is also going to send out inhibitory signals. So by that, you already know that the posterior canal is going to be the one that's sending out these inhibitory signals. Just like with all of the other connections, the next stop for these connections or for these inhibitory signals is going to be in the vestibular nucleus. And this one changes things up a little bit. It's not going to synapse in the medial portion of the vestibular nucleus. These connections are actually going to synapse in the superior portion of the vestibular nucleus. And so we'll just say S here. They're going to synapse their superior portion of the vestibular nucleus here. So SVN. These signals are then going to stay ipsilateral. Because remember, as before, if we're doing upward chin acceleration, eyes are moving down, what we need to do is inhibit the antagonistic muscles. And these would be the muscles that are responsible for us making our eyes look up. So those would be the superior rectus and the inferior oblique. We need to inhibit these muscles. According to Sherrington's law, we need to inhibit them a proportional and equal amount, or a proportional and simultaneous amount of relaxation, effectively so that they relax at the same amount that the agonists contract, and they relax at the same time that the agonists contract, just so that we can have a nice smooth motion of our eyes. So we have gone from the posterior canal to the superior portion of the vestibular nucleus, and now these signals are also going to utilize the MLF and ascend to the layer of the midbrain and then exit. And they're in fact going to synapse onto the oculomotor nucleus. Again, think about which cranial nerve nuclei is stimulating these muscles here. And so inferior oblique and superior rectus are both controlled by the oculomotor nucleus. So the inferior oblique, those connections are going to stay ipsilateral, and it's just going to make its direct connections there. The superior rectus, as you'll remember from our downward chin acceleration video just a minute ago, is going to go to the opposite side and innervate the opposite's superior rectus here. So this signal is in fact going to travel to the opposite side and innervate the contralateral superior rectus. So let's look at this from a ipsilateral contralateral perspective for the canal that was stimulated, or from the perspective of the canal that was stimulated. If the right posterior canal was stimulated, It's also going to send out inhibitory connections from that same canal. Those connections stay ipsilateral through the vestibular nucleus, ascend via the ipsilateral MLF to the layer of the midbrain, and then exit the MLF. They're then going to innervate the ipsilateral oculomotor nucleus. This nerve is then going to innervate its own ipsilateral inferior oblique, but it's going to innervate as well the contralateral superior rectus. So make sure that you kind of get those ironed out, which connections stay ipsilateral according to the canal that was stimulated / inhibited, and which stay ipsilateral, which stay contralateral there. So let's do the other side here, just like almost like real time as if it's happening here. So the posterior canal is being stimulated by upward chin rotation. It's also going to send out inhibitory signals, again, to the superior portion of the vestibular nuclei, so the SVN. Those canals, or those connections, are going to stay ipsilateral and ascend via the MLF, the layer of the midbrain, where they're going to get out and going to innervate the oculomotor nucleus. This has two connections here. One connection is going to go straight to its own inferior oblique. The other connection is going to decussate within the brainstem, and then it's going to come over here and innervate the contralateral superior rectus. So this is in fact both the excitatory and inhibitory signals pathways for upward chin rotation and the associated VOR eye movements or counter rotations to the head rotation. So I hope this video was helpful for you. Please, as I said before, let me know if you have any questions or any comments or suggestions about the video. Otherwise, I will see you at the next video.